Imagine a chef baking a cake. They carefully select the finest ingredients, meticulously following a trusted recipe. Now imagine a mischievous child sneaking into the kitchen and adding a spoonful of salt to the batter. The cake, once destined for greatness, is now ruined, the taste irrevocably altered. This, in essence, illustrates a model poisoning attack. In the world of artificial intelligence, data is our ingredient and algorithms are our recipes. We train AI models on vast datasets, teaching them to make predictions and decisions. Model poisoning attacks occur when malicious actors tamper with this training data, introducing carefully crafted poisonous samples. These poison samples act like the salt in our cake, subtly altering the model's learning process and ultimately compromising its integrity. The consequences can be severe. A poisoned model might misclassify spam emails as legitimate, leading to phishing attacks. Or in a self-driving car, it could misinterpret a stop sign as a speed limit sign, leading to potentially fatal consequences. As AI becomes increasingly integrated into our lives, understanding and mitigating these attacks is paramount. Just as there are many ways to spoil a dish, there are various techniques employed in model poisoning attacks. Let's explore three primary types. Label flipping. This attack involves subtly altering the labels associated with the training data. For example, an attacker might take images of cats and label them as dogs. When the model trains on this poisoned data, it learns to associate the characteristics of a cat with the label dog, leading to incorrect classifications. Backdoor attacks. Imagine our mischievous child adding a secret ingredient to the cake batter, one that only activates under specific conditions, like adding a pinch of chili powder that only releases its heat when lemon juice is added. Similarly, a backdoor attack involves poisoning the training data with a trigger. This trigger could be a specific pattern, a hidden code, or even a unique combination of features. When the model encounters this trigger in new data, it activates the backdoor, causing it to make a specific, predetermined misclassification. Gradient manipulation. This attack is more sophisticated, targeting the very process by which the model learns. During training, models adjust their internal parameters based on the gradients calculated from the data. Attackers can inject poisoned data that manipulates these gradients. This forces the model to learn in the wrong direction, ultimately leading to inaccurate predictions. Detecting model poisoning attacks requires vigilance and a keen understanding of both data and algorithms. Here are some techniques that can help us unmask these subtle manipulations. Data sanitization. Just as we wash our fruits and vegetables before cooking, it's crucial to cleanse our data. This involves identifying and removing outliers, inconsistencies, and potentially poisoned samples. Label consistency checks. Regularly cross-referencing labels against the actual data can help identify instances of label flipping. This could involve using human review or developing automated techniques to detect suspicious label assignments. Influence functions. These mathematical tools help us understand the influence of individual training samples on the model's predictions. By analyzing these influences, we can identify poisoned samples that exert a disproportionately large impact on the model's behavior. Monitoring loss patterns. During training, we track the model's loss, a measure of its error rate. Sudden or unexpected changes in the loss patterns can indicate poisoning attacks, especially gradient manipulation, as attackers try to force the model to learn in the wrong direction. Several tools are available to aid in detection, including CleanLab for data cleaning, DataShap for understanding feature importance and potential biases, and the IBM Adversarial Robustness Toolbox for testing model resilience against various attacks. Just as we take steps to boost our immune systems, we can implement strategies to protect AI models from poisoning attacks. Robust training. Just as our bodies develop antibodies to fight off infections, we can train AI models to be more resilient. Techniques like adversarial training involve deliberately introducing small amounts of carefully crafted poison during the training process. This teaches the model to recognize and resist similar attacks in the future. Access control. Limiting access to the training data and the model itself is crucial. Just as we lock our doors to prevent intruders, robust access control mechanisms can prevent unauthorized modifications to the data or the model's parameters. Data provenance. Keeping track of the origin and history of our data, much like tracing the journey of our food from farm to table, can help identify potentially compromised sources. Understanding where our data comes from is essential in ensuring its integrity. Model explainability. The ability to understand how and why a model makes certain predictions is vital. By making AI models more transparent, we can more easily identify and correct suspicious or biased decision-making processes, including those caused by poisoning attacks. The fight against model poisoning attacks requires a multi-pronged approach. By implementing these defensive strategies, we can build more robust and trustworthy AI systems, ensuring that the cake we bake, so to speak, is both delicious and safe to eat. Data scientists and AI developers must prioritize these defenses, integrating them into their development pipelines and workflows. The future of AI depends on our ability to build systems that are not only intelligent but also secure and trustworthy. Let's work together to ensure that the AI revolution is one built on a foundation of integrity and resilience.